Now what we're going to do today is we're going to do this section 2.4 over specifically linear functions. Now this is likely going to be a bit of a review for you, but I think it's important to cover. For a couple reasons. One of them is that linear functions form one of our most basic types of functions. And two, it helps introduce us to the idea of graphing. And then we're going to spend a little bit of time at the end of chapter 2 here getting into some heavy details with graphing. So let's dive in. A function is linear if, so we defined a function last time, so we should be comfortable with the concept of a function. If you can write the function like this, f of x equals mx plus b. Let's break that down for a moment. First of all, we see the word line. We see the word line is embedded in the word linear. You can see that. That is not just a mere coincidence. That's actually entirely telling, because whenever we graph linear functions, we are just going to be graphing lines at the end of the day. Lines, lines, lines. We're going to see in the moment, I'll write it out, that m is called the slope of the line. Why do they use m? That's actually a good question. I've never really known. It's just, I don't know, that was someone's fancy, whoever wrote this. And then b is going to be the y-coordinate of the y-intercept, the point where the function crosses the y-axis. But we'll cover that again in detail. Here, a few interesting things. If the slope is not 0, so if the slope does not equal, and so we're going to make an equal sign and just cross it out. If the slope does not equal 0, the domain and range are both all real numbers. The entire number line, which you may recall can be written as negative infinity to positive infinity. And that's actually interesting. That's not always true. The domain being all real numbers, get out of here. We talked about last time some of the cases where that wasn't going to happen, especially if you're bringing square roots into it, if you're dealing with rational functions where you're dividing and your variables in the denominator, there's a chance that that's going to break up your domain a little bit. But for linear functions, as long as you have a non-zero slope, you're good to go. What else? M is said to be the slope of the line. Which that's going to tell us basically how steep is the line. And so zero slope is a flat horizontal line. We talked about that last time. Also, the sign of the slope, positive or negative, is going to tell us whether it's basically going uphill or downhill. Now, here is the million-dollar question. People always want to say, it's so tempting to say, B is the y-intercept. B over here, that's the y-intercept. And that's the meat and potatoes of the y-intercept. But the y-intercept has to be an entire coordinate. And that is something that we do kind of, mathematicians, math people, we do become a little bit sticklers about. So you don't just say B is the y-intercept. You say the coordinate 0, B is the y-intercept. So that's not so bad. It's not so bad. Let me record that attendance information real quick. Give me just a hot second so I don't forget. So yeah, we have the slope, we have the y-intercept. Again, this should be review for you, but it's important, I think, to kind of really define our terms, make sure we're on the same page. yada, yada, yada. So let's kind of see this in action. We want to interpret slope appropriately. The slope. Sometimes the slope is referred to by kind of a somewhat famous saying. You guys have probably heard it. Rise over, you're probably finishing it in your mind, rise over run. In other words, well, never mind. In other words, the slope tells us how much the line goes up or down for every change in the horizontal direction. What is the change in the vertical direction? Basically as a ratio to the change in the horizontal direction. So for instance, if you have a slope, let's look at a few quick examples. Let's say you had a slope of 2/5. 2/5. I would interpretation. I would interpret that as, well, first of all, it's a positive slope. Keep that in mind. Overall, it's that 2/5 is just a positive number. So that means for every 5 units you go to the right, the line rises 2 units. It goes up, which means as I go from left to right, it looks like it's on an uphill trajectory. How about a slope of -4 over 9? Let's make it more interesting. I know what you guys are saying. You guys are saying, how can it get more interesting than -4 over 9? Well, -9 over 4, huh? Yeah. Now the overall slope is negative. It's tempting to just say only the negative number is on top, the -9. And yeah, that's true, but that just means the entire fraction is negative. And so the interpretation of that is that for every 4 units I go to the right, the line falls 9 units, not u-naughts, units. The line falls 9 units. So again, rise over run, but it could be fall over run, I guess. I wish I was overrun by fall because fall is my favorite time of the year. I'm very excited for September, October, November. It's just amazing. Halloween, get out of here. What if you had a slope that was just a whole number, like 7? Just 7 will. Just tell yourself it's 7 over 1 there, Pilgrim. And then it's the similar interpretation. For every 1 unit you go to the right, the line rises 7 units. What if we dealt with that slope, and this was tempting to dance around, now let's deal with it. What if you have a slope of 0? Well, if you have a slope of 0, you could use the same terminology here. You could say that's secretly 0 over 1. So for every 1 unit you go to the right, the line, well, it's not going to rise and it's not going to fall because it's 0 units in the vertical direction. So the line doesn't go up or down. It's a flat line. Now let's see, I received a text. Let me check that. So yeah, That's basically the interpretation of a slope of 0. It's going to be a flat line, and flat in the sense that it's horizontal. And so we kind of talked about that last time. So with that in mind, with this interpretation of slope and kind of understanding that a y-intercept is just where it crosses the y-axis, let's graph y equals 3x minus 4. And we'll actually be graphing several different lines here today. All right. Our slope is, well, what do you guys think it is? What do you guys think the slope is here? 3. Yeah, it's the value in front of the x term. A slope of 3. So again, the interpretation using our previous vernacular, our interpretation is that for every 1 unit I go to the right, because you can always write it as the fraction 3/1, for every 1 unit I go to the right, the function rises 3 units. It's going to go up. And then our y-intercept, here's where we shall not fall into that evil trap. It's not -4. No. Remember, it's a coordinate. 0, -4. And yes, we are sticklers for that. We do harp on that. All right, so now let's produce a graph here. We have our y-axis, we have our x-axis. Let's put some divots on there. How should we do that? Yeah, that's fine. I'll put 5 divots. You know, I think it's fun to produce our own graph like this. It makes for some more interesting interpretation of graphs. It gives us a better understanding, I think. 3, 4, 5. It gives us a moment to talk about what's going on in our lives. Nothing much going on in my life because I'm not a very interesting person. You've probably figured that out by now. You're like, oh, probably not a very interesting man, and you're correct. I'm not. Very boring. My fantasy team, my fantasy football team lost this week, just like it lost in week 1. So that's not fun. There we go. So we got ourselves a pretty functional graph here. So the first thing we want to do, let's graph this line. Let's graph it in purple. Why not? So you're going to want, if you're using this style to graph the line, the interpretation of the slope and the y-intercept, that's cool. Start with graphing your y-intercept. In this case, it'd be 0, -4. So starting at the origin, you'd go down 1, 2, 3, 4 units, and here's going to be the y-intercept, that point. Now we want to get a second point on that line. So here's what we're going to do. We're going to use the slope interpretation. This is true if you're going from any point on the graph to another point. It's going to be, well, 3/1. So every 1 unit I go to the right, so heck, I'll just go ahead and start drawing the line. For every 1 unit I go to the right, I'm going to rise 1, 2, 3 units. There we go. So here is a second point on the line that I can use. And it goes on and on and on. If I started from this point, I'd go 1 unit to the right, 3 units up. So ultimately, that's going to be how we graph the line. Of course, it goes on forever in each direction. So in order to illustrate that, I'm going to have to just something like this. Let's see. There we go. That's not so bad. And bada bing, bada boom. You go 1 unit to the right, 3 units up. There's another point on the line, give or take. And then we'll put arrowheads on the line to imply that the line goes on forever and ever in each direction, as it does. And so now we see the graph of this. We can see, yeah, as long as you have these arrows and the line's going to keep going and going and going and going, like the Duracell rabbit or whatever it was called, you're going to see that the domain is going to be all real numbers because I can go anywhere I want along the x-axis and I'd be able to go up and find a point on the line associated with that. Same along the y-axis. I can go all along the y-axis and I'll find points on the line for any point on the y-axis I want. In other words, the domain and range are all real numbers. That's cool. All right, so that's good to do that kind of interpretation. If our slope was -2/5, but I had the same y-intercept, I would go over 5 units and down 2 units. So I'm just appealing to the rise over run nature of the slope. That's kind of interesting. Is there anyone in there who's planning to maybe, when you go to college, study engineering, or how many of you think you might go on and take calculus someday? Any calculus heads out there, maybe?
Yeah, like one person.
Definitely one person is going to. Very good. Well, hey, that is awesome. I applaud you for studying calculus. Calculus sounds scary. You're like, oh, calculus. I promise you that as long as you come in with the proper background knowledge, and that's a big, big issue, but as long as you come in with the right background knowledge, calculus is a middle of the road in terms of difficulty. I would argue there's parts of college algebra that are more of a what or a more difficult than calculus. Seriously. So calculus is not so bad, but if you don't come in armed to the teeth with all the math you learned before it, calculus can seem a lot harder than it is. At any rate, one of the things we're curious about in calculus is rates of change. How much do things change? So basically, how fast is the function increasing or decreasing? What is the y value doing for every change in the x value? And what we find in calculus is that's a very sensitive issue. And for different types of functions, it's not so easy to deal with. But for a line, the slope of the line is actually the rate of change. Because it's openly telling you how much y changes for every change in x. So that's actually a really cool idea. And if you go on to calculus, you'll see it's related to something called the derivative, which is one of the 3 major concepts you focus on in a standard Calculus 1 course. So keep that in your mind. In fact, we're going to look at something that is awfully similar to the definition of a derivative in this class just in a few weeks. And we're going to see it's also not so bad. Okay, so real calculus heads know about rate of change. Let's talk about, well, Mr. Gunther, what if basically we wanted to give you 2 points on a graph, and I mean any 2 points. Let's say that they're distinct points. They're not the exact same point repeated. Of course, why would you want to do that? But you could. Let's say we have 2 distinct points. And let's say we want to build up the equation of that line, that linear function. Okay, well, the first thing you're going to have to do is have some kind of way of finding the slope of that line. So the slope of the line containing or rather I should say connecting is probably a better word, though they're both correct. Connecting the distinct points. And now they use kind of a weird vernacular for it. They're going to say those points are called x1, y1, and x2, x-mid united y2. So any 2 points you want, we'll call the first one x1, y1, and that just means the x coordinate of the first point, y coordinate of the first point. This is the x coordinate of the second point, y coordinate of the second point. People get hung up on this, and I could have called it A, B, and C, D if I wanted to. I could say the first point we'll just call it A, B. Second point we'll call it C, D. We're just using variables to represent the points. And in this case, we're just using subscripts on there. So that the slope connecting those 2 points, slope of the line, is given by the very famous formula. Slope is y2 minus y1 over x2 minus x1. In other words, it's actually just going to be the change in y over the change in x. How much does y change? How much does the line change in the vertical direction for every change in the horizontal direction, change in x? It's just a ratio of the two. That's all it is. That's pretty much almost just straight up by definition. And again, we're going to see that that has some very powerful implications in calculus. So a simple example, find the slope of the line which connects the 2 points. Let's say those points are -3, 17. And I'll give it a little space, a little breathing room. And the point 4, 3. Well, all right there, Pilgrim. Let's see, this is the first point that is provided. So let's just not even beat around the bush. Let's call that x1, y1. So x1 is -3, y1 17. Let's call this point x2, y2. So x2 is 4, y2 is 3. And now our slope equation is y2 minus y1 over x2 minus x1. Now bear in mind, this is subtraction here. This is minus y1. So if you're subtracting a negative, don't try to say, oh, well, I'm already doing subtraction, and only do one minus sign. If you're subtracting a negative, you need to realize that I'm going to end up adding, basically. So y2 minus y1, so that'll be 3 minus 17 on top. x2 minus x1, that'll be 4 minus -3 on bottom. And again, it is so tempting to make this mistake here. It is so tempting to just say, oh, it's just 4 minus 3 because this was already -3. And guess what? You would be incorrect in that case. And trust me, you think when the rooster crows 3 times, one of you will betray me. I promise. I'm just kidding. But it's so easy to make that mistake. So try not to make that mistake. Okay, so we just have a little calculation to do. Let's see, 3 minus 17. I know it's going to go negative, and then it's really just 17 minus 3 once I've dealt with the negative sign. 4 minus 3 becomes 4 plus 3. So overall, this slope becomes -14 over 7, which reduces to -2. -2 over 1. All right, that's groovy. So we would just have a slope of -2. So let me kind of bring up the highlight reel here. And I will banish this to the 9th dimension of torment. So we have a slope of -2. What that means, of course, is that for every 1 unit I go to the right, the line falls 2 units. So it's going down. It's like it's going downhill. So let's talk about the 4 types of slope. We already briefly mentioned it last time, but I want to go into detail again on that. The 4 types of slope. In this case, what we would have you'd have that situation if you had a negative slope. The thing's falling as I go from left to right, because this is America, baby, and we read from left to right. So we also are going to look at our graphs from left to right, which makes sense because that means if we're going along the x-axis, the numbers are increasing. And of course, you can, if you want, you can put arrowheads if it's not clear that the line's supposed to go on forever. You learn, you learn about lines and rays and line segments. I don't know if you guys remember that. Um, that's something that you don't ever really see again. So a line is defined as automatically having these arrowheads and going on forever in each direction. So that's all it is. Remember, a ray, you might argue that, a ray is one that goes on forever just in one direction, not the boy band, but ends at the other and just stops there. That's just something we don't ever really revisit as you keep going down the trail in math. So this is what a negatively sloped line will look like. It's falling. All right, so let's make it more interesting than that. Let's talk about what a positively sloped line looks like, and you're going to see some fun stuff. So find the slope of the line connecting, how about the points? 4, comma, -9. And how about 1, comma, -16? That works for me. All right, Will, it's probably a good habit to just say the first point you see, call it x1, y1. Second point you see, call it x2, y2. And you don't lose any sleep over it that way. So first we'll go ahead and compute the slope of that line. Let's see, m is going to be y2, which is -16, minus y1, which is -9. On bottom, 1 minus 4. All right there, Pilgrim. -16, that becomes -16 plus 9, essentially. On bottom, you'll get -3. -16 plus 9, it doesn't save it from being negative. And then just think, I'm starting at -16, I got to move 9 units to the right. So you can think of it like that on a number line. I end up with -7 divided by -3, but again, that's a negative divided by a negative, which is positive. Now, the 7/3 doesn't simplify any better than that, but I can at least, you can tell yourself I'm canceling out the negatives. That's fine, but it's the same thing in spirit as now positive 7/3. So now we have a positive slope. So let me bring that up here to bear. We have a positive slope. And now you could probably imagine what a positive slope looks like. We don't need to tarry on too horribly much here. Positive slope. All right, it's going to look something like that. Again, with implied arrowheads. Now, it may not look exactly like that. You know, it can cross the y-axis anywhere along the way. It can be steeper. Your line could be a lot more steep than that, or it can be a lot more chill. It can be a little flatter. But ultimately, a positively sloped line is going uphill as you go from left to right. Pretty simple concept. And we can see it from the interpretation of the slope. Go 3 units to the right, 7 units up. That's kind of what's happening here. But there's 2 other types. We did discuss it last time, so I won't go on too horribly long about this. A horizontal line, but let's go even further with it this time. So I'll give you an example of a horizontal line, but then let's talk about how we construct the equation of a horizontal line. Now let's find the slope of the line connecting. So what we're going to see is that the telltale characteristic of a horizontal line is that for any 2 points on the line, they're going to have the same y coordinate no matter what. So I can pick negative 100 for the x coordinate, comma, how about 4 for the y coordinate? And then I can pick, oh, I don't know, 36 for the x coordinate on my next point. But since I'm trying to construct a horizontal line, the y coordinate needs to be the same in both of them. Well, all right there, Pilgrim. So the slope would be y2 minus y1. Again, I'm just going to go ahead and write x1, y1, x2, y2. Because like I said, that's a good habit to get into. So it's going to be on top, 4 is y2 minus 4 again. On bottom, I guess I'll get 36 minus negative 100. Well, wait a minute there. You're going to get a 0 on top. 36 minus negative 100 becomes 36 plus 100, but that doesn't matter. You're going to get 136 on bottom. And 0 divided by any non-zero number just turns out to be 0. It just negates the whole thing. So again, the interpretation of that is for every 1 unit I go to the right, the thing, well, I can't say it rises 0 units. That doesn't make sense. The thing doesn't change in the vertical direction. And so this will be my slope here. That's going to create a horizontal line, and it's just logically it makes sense. You have this, and you know what? Let's make this a nice long x-axis here, and I'll even demonstrate why that makes perfect sense. Let me straighten this out. Come on, get in line there. Literally in that case, right? Let's see. Let's say we have our 2 points. We have negative 100 comma 4. So it's a very large but very extreme x value along the negative side. And let's say it's that point there. I'll even label it. That is the coordinate negative 100 comma 4. 36 comma 4 would be like over here. Something like that. And that's the point 36 comma 4. And again, remember, we've gone from one x value to another, and we haven't changed the y values. So the thing hasn't gone up or down. And that's exactly what a flat line looks like. So, bada bing, bada boom, that's a flat line. Again, you know, it's parallel to the x-axis. You'll have to forgive my shortcomings in drawing, because I do actually think it's helpful to show you how this is done freehand. I actually believe that. I'm a very strong proponent of that. I believe that the less you leave to computers, the more kind of skills you're actually developing, skills native to your own mind. And I think that is very important. Anywho, we get that, and what we can see is that's just a flat or horizontal line. But what's going to be more interesting, something I didn't really get into detail last time, is how do we construct the equation? How do I construct the equation of a flat line? Well, remember the general, I'll do it two ways. The general equation of a line was mx plus b. M is the slope, x is going to be the general variable, x, and it stays x. B is the y coordinate of the point where it crosses the y-axis, the y-intercept. But wait a minute, we're saying the slope is supposed to be 0. So it's 0 times x, which of course means it's going to get wiped out altogether. And then here, we'd want to know this, the y-intercept. The y-intercept will always have a coordinate of 0 for x. And then look at this, the y's values are supposed to always be 4. It's a flat line, you're never going up or down. Thus, the y-intercept is also that 4, it's 0, 4. So our equation would be 0x plus 4. And so I'm doing 0 times x. It doesn't matter what x is, as long as it's a finite number, which it will be. I just end up with the number 4. Put another way, the equation of a horizontal, or I'll just say a flat line, is going to be f of x equals some constant, b, where b, remember, is the same b as up here. It's the y coordinate of the y-intercept over here. So anytime you just see that, or remember, we can interchange f of x and y. If you ever just see y equals, and it's just some number, y equals 3, y equals negative 15, that is going to be a horizontal or flat line when you graph it. And so that means that this line here specifically would be the equation y equals 4. So that's pretty cool. Of course, another way to argue that is to say that no matter what x value you pick, you can pick negative 100 for x, you could pick negative 2 for x, 0 for x, 36 for x. No matter what x value you get, the function always spits out a 4 for y. So you can just say, well, just y equals 4. X isn't even in there because x is arbitrary now. I can pick any x value I want, and I'll always get a 4 for y. So I think that's pretty darn cool. I think hopefully all of you out there agree with me. So flat or horizontal line. Finally, let's look at what it takes to make a vertical line. And what we're going to see is we kind of talked about it last time again. Find the slope of the line containing or connecting. Now, a vertical line is going to have the same x value, and now the y value can be whatever it wants. So I just need to pick 2 points that have the same x value. How about negative 5, whoops, comma, and then I can pick any 2 y values I want. I can go a little bit crazy here, but oh gosh, 125, oh man, can I do that? I think the math police are going to be arresting me later. Yes, you can do that. You can do whatever you want and go a little bit wild. 10.5, oh my goodness, we can bring that into it. We sure can. So now what we'll see, let's use something different than purple. Let's use orange. This is x1, y1, x2, y2. So the slope is going to be 10.5 minus 125 on top, negative 5 minus negative 5 on bottom. And now you can see the problem. So 10.5 minus 125, you can see that's going to go negative. Then 125 minus 10.5, you might be able to see that's going to be what, 114.5. But the top here is actually not going to be all that interesting to us. The bottom goes to 0. Whoa, Nelly. We've argued before you can't divide by 0. Which means that we are actually going to have undefined slope here. The slope is not 0. The slope, some people are tempted to call it infinity. Perhaps you can think of it like that. But at the end of the day, what you have is, when you graph it, now you have 2 points. Let's see, those 2 points are going to be -5, 125, so maybe that's way up here. -5, 10.5, maybe that's down here. But again, since you have repeated x values, they're right. One is right above the other, if you think about it. And so what you get is a vertical line, and I'll redraw the line here in just a moment. I'll put this point. Come here, Yush. I believe. There it is. Yeah, you're going to have a straight up and down vertical line. Bada bing, bada boom. So undefined slope goes with vertical lines. The equation of it, you actually can't write it in f of x mode. And there's reasons why. I won't go into uber detail about why. But at the end of the day, the equation is going to be an x equals equation. Why is that the case? Well, in this case, let's see, it's going to be x equals -5. So anytime you have x equals some constant, that is the equation of a vertical line. It makes a little sense because that's saying, look, y is not involved in this equation. In other words, no matter what y value you want, the x value is always -5, no matter what. The x value is always -5. And so you can see from the points there. So that's kind of the justification behind why we write the equation of a vertical line like that. So if your 2 points were 3, 15 and 3, 27 million, your equation would be x equals 3 there. It's all about the x coordinate you have. So let's graph a couple more equations. Let's look at some graphs. And again, I like drawing these virtually by hand because I'm actually doing it with a computer, but you know what I mean. I'm doing it, it's me doing it, it's not some tool doing it for us. And let's say I want to make 10 divots in each case. Let's say that they're there, but drawing them is going to get a little tenuous. But let's say as we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same up here, 1, 2, 3, 4, and then this will go negative. -1, -2, -3, -4, -1, -2, -3, -4. So we're going to start graphing a few things. Let's do like a graphing lightning round. How about the equation OY equals -4 over 5x plus 2. So let's do a lightning round. This will be the red line. I would start with 0, 2 because I can just immediately see the y-intercept is 0, 2. So from here I go up, let's say 1, 2 units. So somewhere around there. 0, 2, very nice. And now the rise over run interpretation, -4 over 5. Okay, so let's put it in our brains. For every 5 units I go to the right, so let's say 1, 2, 3, 4, 5. So mark that. I'm going to fall 4 units because it's negative. So 1, 2, 3, 4. And I'll get something like that. You can also create the points for this, and this is where it's really cool. We already knew this was the point 0, 2. The second point, I went right 4 units, so I increased the x value. Excuse me, I went right 5 units, so I increased the x value to plus 5. So I went from 0 to 5. The y values, I decreased it by 4 units, so 2 minus 4 becomes negative 2. And that's our second point there. And now I just need to draw the line, connecting them, and then of course that line goes off in this direction as well. That's a little harder to draw in one fell swoop. The cool thing is your MyLabs Plus homework, you will be graphing some lines in this section. And it's really nice. You're going to have a line grapher tool, which is going to say, oh, pick a point on the line, pick a second point, and then it automatically like draws the line. So you're actually just picking 2 points on the line, which is pretty neat. So bada bing, bada boom, that's the line, negative 4/5 x plus 2. Do y'all want me to go through a couple more examples of graphing? What do you guys think? Whoever shouts a reasonable shout. Go ahead.
Yeah, we're good.
Y'all are good. Very good. So we got through the basic bit of stuff, the mucky muck, as Jack Black would say. And now let's get into some stuff that's a little bit more interesting. So let's say you're on a road trip. Let's not use red. You're on a road trip. And let's say you set the cruise control. You set the cruise control, meaning you guys probably know what cruise control is. Of course, if you had a car built or made before like 2005-ish, cruise control was not guaranteed in your car. When I was in high school, I had a car that did not have cruise control, and it wasn't very fun, but I guess it made me pay attention to my speed a little more. So you set the cruise control, that's going to set a speed for you. Let's say that you're on a relative flat road, and let's say you're just going to drive the same speed. Let's say you drive the same speed the whole way, and then we're gonna change those assumptions in a moment. So on a road trip, you set the cruise control. After 3 hours of driving, let's say you're on the same highway the whole time. After 3 hours of driving, you hit mile marker 167. So if you've been on a highway for long enough, you know there's mile markers. What does that mean? Usually that means you're 160, if it's an interstate, you're 167 miles from from the nearest state line. That's usually what that means, but not necessarily, it's a little complicated. So let's just say for now, that's just an arbitrary point to say, oh, if you got in an accident and you need to call the ambulance and you're in the middle of nowhere, you can say, I just crossed mile marker 167 heading westbound on I-20 or something like that. And that's something they're going to use to locate you. But the cool thing is the difference, if you go from mile marker 167 to mile marker 187, there are exactly 20 miles between those. So they're not completely arbitrary, but that's kind of what they're used for. Let's say after 7 hours of driving, you hit mile marker, let's make it interesting. Let me think what an interesting one would be. How about 375? Assuming you drove the same speed the entire way, what was your speed? Now, you're tempted, and probably justifiably so, you're tempted to just say, okay, well, I can tell you how many miles I drove. I drove whatever 375 minus 167 is. That's how many total miles you drove. And I did that in 4 hours, because from hour 3 to hour 7, that's obviously a 4-hour difference. So I would just take the number of miles I drove total divided by however many hours I drove. And guess what? You're tempted to do that because that's exactly correct. That's exactly what we're going to do here. But I'm going to put a little twist on it. And I want us to write all that out using what we've been learning here today and putting it in the scope of being, of being linear. So let's think. Let's put on our math brains. Let's think. We usually speed. You may have heard the term velocity. Velocity is just speed, then with a direction attached to it. It's called a vector quantity. Speed is called just a magnitude quantity. But we're not going to worry about that. Speed, how fast you're going, not the movie about Sandra Bullock on the bus. Speed is usually measured in some unit of distance over some unit of time. Of course, here in the US of A, we use miles per hour. The word per makes us think of division. You see the word per, you're thinking division, and that's exactly right. So just using a little bit of what I think is either common sense or sense that you've maybe developed, especially if you are a driver, you can usually measure your speed as miles driven over time to drive that many miles, or number of hours you drove. If you drove only 15 minutes, you could say that's a quarter of an hour. So if you drove 10 miles in 15 minutes, you could say it's 10 divided by 1/4, which actually becomes 10 times 4, or 40 miles per hour. So it is consistent no matter how you do it. So you're tempted to just say, well, I drove 375 minus 167 over 7 minus 3. That's exactly right. But here's what we're going to do. We're going to interpret the slope appropriately. We're going to interpret the slope of the line, get all of it, appropriately. Come on. You can grab all of it. I don't know why it doesn't want to grab everything here. That's okay. I'll just manually adjust it. Here's what we will do. We're going to write our two pieces of information here concerning number of hours driven and mile markers. We're going to write them as 2 points. We're going to write them as the points 3, 167. Why did I write 3, the number of hours, as the x variable and 167 as the y variable? There's a couple ways to justify that, but we're going to see that in a moment when we do the slope calculation. That's going to put the miles business on top, which is what we want. That aligns with our usual understanding of how speed works. And then on bottom, we're going to have the number of hours driven. So that actually makes perfect sense to write the coordinates this way. So we'll say that's the point 3, 167, and then that makes the other coordinate 7, 375. So now we'll calculate the slope of the line between them. So remember, we're going to call this x1, y1. I'll even write it just so we get into a good habit. x1, y1, x2, which is coming to Disney Plus soon, y2. Okay, so it's y2 minus y1 over x2 minus x1. But we don't have a calculator. But you don't need a calculator on this one, especially. 375 minus 167. Maybe you can do that one in your head and see it'll be 208. Of course, you're always free to come out here to the side and do 375 minus 167 using kind of your old school subtraction techniques. That's fine with me. Can't do 208 divided by 4 in your head? No worries. Do long division. And you'll see it comes out to 52 rather cleanly. It's going to come out to 52. So, but I need that space back. So you're going to get 52. So 52. So wait a minute. We can answer the question, but we want to interpret it better. Assuming you drove the same speed the entire way, what was that speed? Well, it was 52 miles per hour. That's pretty cool. But this actually has some rather far-reaching implications. This means that the slope of the line connecting points that involve time and distance driven is the speed. But we already argued that slope was a rate of change. So speed or velocity, speed is the rate of change of your distance traversed or distance traveled. That's actually kind of interesting. That's actually really interesting. Again, if you go into calculus, you're going to be revisiting this. Now, what if we wanted to relax this assumption here? Assuming you drove the same speed the entire way. What if we wanted to relax that? Assuming nothing. Let's just completely cross that out. Let's instead say you decided to make some stops because 52 miles an hour, if you're on a road trip and the speed limit on a good interstate is usually around 70, at least 70. So 52 miles an hour is not really making good time if you're allowed to drive 70 the whole way. But maybe you made some stops. Maybe you made a few stops. Maybe there were some parts where you were able to drive a little bit faster. Maybe you hit some traffic. Maybe you hit some construction. You had to slow down a little bit. So what if you weren't driving exactly 52 miles per hour every second of that trip, which is realistic because even with cruise control, like I said, there's so many factors that are going to affect how fast you can drive. But let's say no matter what, still after 3 hours of driving, you were at mile marker 167. After 7 hours, you're at mile 375. What does this 52 miles per hour mean? It still has an interesting interpretation. It was actually just your average speed. It's how much you averaged on that leg of the trip. And in turn, we're going to see that the slope is actually something called the average rate of change. The average rate of change is another word for slope. Even when you don't have a situation that is actually creates a line when you graph it, you can still calculate the slope between 2 points. And it's just going to tell you something different. It's going to tell you like average rate of change. So this is actually a really interesting example. Now you're starting to see the wheels turn. Well, if you're a rocket scientist, if you're working for Lockheed Martin, and you want to model things like how fast does your rocket change, or rather your airplane maybe, how long does it take to get from point A to point B? You're going to naturally start talking about miles, time, things like that. You're going to talk about speed. You're going to have to model those things mathematically, and then you're going to end up bringing calculus and some more advanced mathematics into the game. But look, those kinds of things can be modeled with math, absolutely. I wouldn't think twice about modeling something like that with mathematics. So you can see why a lot of engineers, if you're going to study engineering, a lot of engineering just involves math. Like there's no way around it. Another interesting modeling example. Let's say you're running a business. Let's say you are running a business. Let's say, there's the classic lemonade stand thing. That's not really, that's a little too classic for me. Let's say you're selling widgets. That's an old line for saying you could be selling anything. There's no such thing as a widget. It's just an old math joke that you just call it a widget so you don't have to think of something specific. Let's say you're selling widgets for $15 a piece. That cough actually came out a lot louder on my headphones, so I kind of jumped in my chair a little bit. That's okay, though. Not your fault. What's that?
I turned my head away from
Yeah.
So
That's okay. It's no worries. But yeah, so let's say you're selling widgets. Okay, sure. For $15 a piece. But here's the thing, when you're running a business, and now mathematics absolutely has a place in business. If you plan on opening your own business, don't just think, oh, I'll just hire someone else to do the math for me. Well, your business has to be somewhat successful before you have the money to hire someone to do it for you. You have to have at least a pretty moderately advanced understanding of mathematics in order to run a business. There's just no two ways about it. Maybe later on you can just kind of let everyone else run the business and you just collect the profits. But in the early goings, no, you're going to have a lot of math coming at you and a lot of spreadsheets and a lot of numbers. Anywho, let's say you're selling widgets for $15 a piece. Now, here's the thing. You have different types of costs. It costs $7 for each widget you produce. And even that, just a flat $7, even that is not as simple as you think. Even that, like, oh, well, actually, the first 100 widgets cost $7, but after that, the next 100 widgets cost $8 a piece. You know, you're going to get more complicated as you get into a little bit more realistic scenarios. But we're keeping it a little bit basic so we can see kind of how linear functions work. It costs $7 for each widget you produce, which means it looks like you're making a profit of $8 per widget, and we'll get back to that in a moment. So it costs $7 for each widget you produce, but you have an overhead of, I have a number in my notes, but it's not an interesting number. Let me just produce one real quick. Let me do a little side computation. You have an overhead of $7,440, let's say per month. And what overhead is, those are basically called fixed costs. Those are costs you incur even if your entire business shuts down. And unfortunately, during the coronavirus pandemic, we have a great example of that. Let's say you're a restaurant and you have to shut down because you're literally, for the 3 months there in the summer, you weren't allowed to be open. But did magic fairies come and take away all your bills? No, that's not what happened. You had to still pay the rent on the building, assuming you were paying rent on it. Your electric bills probably went down. Some of your bills probably went down, but they didn't go away altogether. So you can think of overhead as fixed costs that you got to pay no matter what. No matter what. So now let's put on our business minds. We're going to have 3 different things that all business owners should understand the concept of. You're going to have something called your revenue. Revenue, we're going to say it's this thing. This is the information concerning our revenue. Revenue is just the raw dollars you're bringing in. Revenue does not look at cost, because you might say, oh, we brought in $1 million of revenue this month. We're millionaires, man. But if it cost you $3 million to run your business that month, whoa, you lost money, didn't you? So revenue is just raw dollars you brought in. It doesn't tell you the whole picture, but it's important to define it. And then what we're going to have is, this is your information concerning your cost. And there's different parts to it even inside of that. But this is cost. This is just how much money you spent to run your business. So those are interesting. What we're ultimately going to get into is that profit. That is the number we're most interested in, because at the end of the day, you're running a business to make a profit. So when I say, hey, I'm making money, I'm not saying I'm making revenue. That's not what you mean when you tell your friends, yeah, my business is doing great. I'm making all this money. You're talking about your profit. You're talking about after I pay off my costs. So profit, very simply, is just your revenue, minus your costs. That's all there is to it. Now, again, this is a very simple example. Revenue, profit, cost, all those things for a business can get really advanced depending on the type of business you're running. Maybe your business sells widgets, but also is a service industry, and you run IT support for other companies. So you're selling a service, and on top of that, you might sell them some laptops that you pre-build for them and has all their programs that they need on it. That would be multiple avenues or multiple different revenues you're bringing in. So for our simple example, we're assuming there's only one way we're bringing in revenue. Well, what we want to do is we want to model these things. Like, this is just begging. This is just begging to be modeled with mathematics. It just is. I mean, you're talking about numbers. Numbers and math go hand in hand, right? So what we're going to do is we're going to set up 3 functions. We're going to set up your revenue function, and I'm going to call it R, and I'm actually going to say R of X. And what we're going to do is we're going to let X be the number of widgets sold in a month. So we're just looking at the revenue, profit, and cost in a month, in a single month of this business. So we'll say the month of, okay, September, that's fine. So now, if X is the number of widgets sold, this is the only piece that goes into your revenue. What is going to be the revenue function here? What do you think is going to go right here, guys? Well, let's see, it's $15. I should probably incorporate the 15 somehow. Ugh, it's a bad 5. Should incorporate the 15, and then it's just multiplied by the number of widgets of the things that I'm selling. And that's all there is for the revenue, 15x. If I was actually selling 3 different things, if I was selling widgets and iPhone cases and water bottles, I could say X is the number of widgets, Y is the number of iPhone cases, Z is the number of water bottles I'm selling. And then whatever their price is for each of them, I would attach that price and add them all up. But in this case, we're only selling one thing, so there's only one variable we're interested in. Now, so this is the revenue function. The cost function, it's also going to be a function of X, because the number of widgets you sell has a major impact on the cost. So it's going to cost me $7 for every widget I produce. So 7 times X needs to be a part of that. And even though costs subtract away from your profit, we're not doing that just yet. We're just seeing what is our total cost. So it's going to be a positive number at the moment. So it's going to be positive 7X. And no matter what, every month I got to pay $7,440, but no more or less than that. So that won't have a variable attached to it. That will not have a variable attached to it. And I have to add it because, again, I'm just looking at the cost like it's a positive number at the moment. Now what I can do is, with these things established as they are, this is called the fixed cost. This is called the variable cost component sometimes because it can actually change. Now I can establish and create my profit function, P of X. And it is going to be my revenue, in this case, revenue function minus my cost function. And when I subtract my cost function, I have to subtract the whole darn thing. And that's a 7 at the front. And I'll close off the parentheses. So now let's bring all this up and let's actually compute the profit function. Let's simplify it. You would distribute the subtraction, 15x minus 7x minus 7440. So now that 7440 is finally being subtracted now that we're talking about profits, because yeah, that's 7440 I lose every month just right off the bat. I can combine like terms here. So it's 8x minus 7440. That's my profit. And now we can start to see the lights turn on. Oh, my profit. Remember, we said it was $15 per every widget that we get back, but it costs $7. So I'm profiting $8 per widget. And now that is where this part comes in. That makes perfect sense. I'm making $8 in profit for every widget I produce. And then I got to subtract off that fixed cost that is always going to be there. So now I've got myself a nice little profit function here. P of X is 8x minus 7440. Let's go even further with that. How many not roads must a man walk down before you can call him a man? Instead, how many widgets must I produce in a month to break even? And here's a hint, you break even when your revenues are the same as your costs. You didn't make any money, but you didn't lose any money. In other words, the break even point is the same as, i.e., when will I have zero profit? You didn't make money, but you didn't lose money, your profit's zero. So in order to find this, I'm literally, X is the number of widgets that I'm producing every month. I'm literally just gonna take my profit function, and what do you guys suppose I will set it equal to? What do you guys think?
This is 0.
It is 0, and you are correct. Very good. And so let's just solve that real quick. We'll add 7440 to both sides. Then we got to divide both sides by 8. Of course, you don't have to do that. In your mind, that's one I cannot do in my mind either. You can use long division. 8 goes in 9 times, so we're gonna have to do that. Carry the 4, 3. We can't stop. We can't just say we have a 0 remainder because we have one more value to bring down. 8 goes into 0 times, and so then you can see there's no remainder. So the answer is 930. So if we produce, and you also have to sell it, you can't just produce it and it lays on your shelves. If we produce and sell 930 widgets in a month, we break even. Of course, since you're pulling a profit per widget, then you have to turn around and you have to, if you sell more than 930 widgets, you'll finally be in the black, which is where you want to be. You'll be making money. You'll have positive profit. If you sell less than 930 widgets, basically what that means is you did not pull enough profit just on the widgets to even cover your fixed costs. So that's it for the day. Thank you guys so much. A couple of you, remember I have my review sessions from 3 to 4 today that you are welcome to come to in the academic building, room 129 on the Weatherford College main campus. And so I look forward to seeing y'all if you plan on coming. Thank you guys.